50. We have the pleasure to start today with the invited conference, and Professor Francesco Paolucci is the chairman of this session.
Okay, thank you, Francesco. It's a great pleasure for me to be here. It's a lovely new building of Diderot. And good morning, everybody, of course, and many thanks to Fetty and the organizer for their nice invitation. They asked me to talk about electrocatalytic reduction of CO2. And so today I will give you a short survey of what we have done in this area since now 20, 25 years. And a large part of this work was made with Raymond Zissel. Stand up, Raymond. Okay, and you can see that there is a question mark in my title, as every good question. It's still an open question, so I have no definitive answer to this very nice question. So actually, everybody is strongly aware about the big problem caused by the massive emission of CO2 in the atmosphere. It's caused by a continuous increase of the human activity. And I don't want today to talk too much about that. Professor Whiteside on Monday afternoon gave some indication, some general trends about it. So I prefer today to show you just a short video. It's coming from French television, an advertisement, and probably most of you know this comic video. It's in French speaking, but the subtitles are in English. So go ahead, if it's works.
Quand nous avons fondé Atmos, notre but c'était de vivre sans rejeter un seul gramme de CO2 dans l'atmosphère. Donc il a fallu tout réinventer. Nous avons renoncé aux énergies fossiles, par exemple, à l'électricité sale, et nous avons refusé tout produit manufacturé. Nous avons banni tout ce qui venait de l'extérieur à cause du transport, et bien sûr nous avons cessé de faire du feu. Et là nous avons atteint notre idéal. 0 CO2 rejeté.
Bien, mais quand vous me parlez, vous rejetez du CO2, pourtant, non?
Pas du tout.
Okay, thanks. That's the main message, of course. And don't be worried. You can continue to breathe. The human breath is peanuts versus the massive emission of CO2. So don't be worried. No panic. More seriously, how people our researcher can address this problem. Actually, the main solution, the main answer is based on a physical approach, a pure physical approach. I mean the storage, the capture and the storage of CO2 in the ground as for fuel, as nuclear fuel waste, okay? But it should be more convenient, probably to be able to use CO2 as a carbon source, as the natural photosynthesis is able to do. The problem is that the CO2 has to be activated, because CO2 is the most oxidized form of the carbon. And it's necessary to reduce or at least activate by a catalytic process. And if you look the utilization of CO2 in industrial process, you can show you here the situation at the end of the last century. There are only 4 commercial processes. And look, the consumption, it's less than 1% of annual release. As I said, there are only 4 commercial processes make urea, salicylic acid, and organic carbonate. All the other processes described here, all the other processes are still at pilot or laboratory scale. And this for process doesn't involve the reduction of CO2. Some other here, involve reduction of CO2. And if you think about reduction, you think immediately, we are electrochemists, you are thinking about electrochemical way to reduce CO2. The problem is that if you have any chance to make this following an industrial process, it's necessary to use a very simple condition. I mean, pure aqueous solution as electrolyte, for instance, and a very usual electrodes. So how to reduce CO2? That's the thermodynamical data at pH 7 in aqueous solution, potential R versus ECS. There are a lot of possible compounds issued from the reduction of CO2. Here are shown the main compounds. Oh, bad quality. Perhaps I have to shift this one. How it works? Okay. So it's depending of the number of electrons coupled with exchange of protons. And for instance, 2 electron, 2 protons, it's a proton coupled electron transfer, of course. No, it's okay. And with the 2 electrons, you can go to the CO. It's a very important industrial compound, for organic chemistry and also to make hydrogen. Formate, which is also a very important starting compound for pharmaceutical industry. 4 electrons, it's formaldehyde, another important compound, and more importantly, 6 electron, 8 electron goes to fuels, methanol, methane. But don't forget that in parallel, you have to avoid the direct reduction of protons. Look the difference of potential here. It's, of course, thermodynamic. And as you can see, the condition to use a convenient process to reduce CO2, protons are needed, selectivity of CO2 reduction versus the proton reduction, and more importantly, potential accessibility. So electrochemists were interested by this problem since a long time, 100 years at least. The first work was made at that period. And they use, of course, obviously, metallic electrodes. There is a talk this morning about copper, I guess. What about the metallic electrode? It's work, more or less, but it's work. Problems are, in general, a poor selectivity, a high over voltage, and usually a cathode deactivation occurs because there is some formation of local carbonyl derivative which prevents the current. So since around 30, 40 years, people were thinking about using a molecular catalyst, and specifically metallic complexes. Why metallic complexes? Because it's supposed to be very important to activate CO2 before its reduction. I mean, if you reduce a complex, the reduced form of the complex is able to bind CO2 to make an intermediate complex, and there is activation at that stage of this complex. It's called inner sphere reaction. So the process can be occur following an homogeneous solution or more important, immobilized on electrode surface. So if you look literature about the molecular electrode catalysis working in pure aqueous solution, there are not a lot. The first one was cobalt phthalocyanide at that moment, or a little bit previously, in fact. And in fact, there is a poor selectivity of CO, production of CO, versus the production of hydrogen. Another example are pyridium derivatives. It's not the metallic complexes, of course. And one of important work was made by Wrighton. It was a film of Viologen incorporated palladium particles. It was not nanoparticles at that time. They don't use the word nanoparticle, but probably it should be. He got nice production of CO, but the electrode is not stable. Why? Because some aggregation occurs during the process, and the activity is limited. Another interesting system is a simple pyridium, but it used hydrogenate palladium or platinum electrodes, and they obtain quite nice quantity of methanol, for instance, and formate. Another interesting system is a polyvinyl terpyridine chrome films. It goes to formaldehyde, is very unusual, 4 electrons, remember? But it's a slow process, and nobody else was able to continue in this, with this kind of electrodes. Another important system is nickel cyclam by Jean-Pierre Sauvage and co-worker. The problem is it's necessary to use a mercury electrodes because the complex absorbs on the electrode surface, and also a monolayer, a long-mirror blodgett, because if you make a film, the film is not enough conductive. There is no possibility to exchange of electron for this kind of nickel cyclam. And the last series, it was probably the most famous. It's a rhenium complex, bipyridine with 3 carbonyl and 1 chloro ligand. The first work was made by Raymond. And, well, in fact, initially, this complex was used as a photocatalyst for reduction of CO2. But it worked very nicely in homogeneous or in a polymer film. We and some others made some films, some immobilized compound on the electrode surface. We and they obtain quantitative formation of CO, but it needs an organic solvent. If we try to use this system in aqueous solution, there is a poor selectivity as for phthalocyanine production of CO versus hydrogen. It's because the potential of reduction is too low. It's too negative. So what we have done in this area, beside films of rhenium derivative. So at the beginning of the 90s, we discovered a new class of compound by pure chance. It's very unlikely material. As Raymond said at this time, impossible. It was impossible. He said that. So our material is a sort of polymer based on a metal-metal bond. For instance, M here is ruthenium or osmium, and each metal is surrounded by one or two carbonyl group and a bipyridine, a diamine ligand like a bipyridine. And there is a flat zigzag chain to arrange all the system. So, how we made that? We made that by electrochemistry, but it's possible to make also by photochemistry or by chemistry. It's just necessary to use convenient reducing agent. So, electrochemistry. It's possible to make film of this stuff very easily by reduction, following a 2-electron reduction from a mononuclear ruthenium complex precursor having 2 level ligands. And this kind of film of polymers are very adherent, electroactive, very important, colored. So just as an illustration, what looks for the electroactivity of a precursor of that time, bis-chloro derivative. It is in acetonitrile, that's the cyclic here, corresponding to the reduction of the precursor. It's the signal here, it's typical of electrodeposition and redissolution of a compound on the electrode surface. It looks like, for instance, copper 2+. It's a bielectronic process, as I said, and with the formation of the polymer on the surface here. And when you go back, there is oxidation, desorption, and dissolution of the corresponding film. Oops. Okay. So, the process is very efficient. It corresponds to quantitative formation of film. And you can follow the formation of the film by continuous scanning the potential in this area, in the catalytic area. You have just to take care about the potential on the way back. You have to stop to return the potential just before the dissolution of the film. And you can see the growth of 2 signals here, quite reversible, corresponding to the electroactivity of the film itself on the surface of the electrode. But you can also, of course, make corresponding film simply by apply potential at that potential. Well, so as usual, it's very common. If you transfer the film in pure electrolyte, after a while, you can observe the electroactivity itself of the film. And as I said, the film is electroactive. That's the rest potential. You start from there, in fact. The film can be reduced. We have demonstrated that later. It corresponds to the injection of the electron of the ligands, and here that's corresponding to the oxidation of in the metal. This kind of film exhibit excellent electrochemical stability if you stop. If the oxidation is stopped at minus 0.6 volt, at that stage there is desorption and dissolution of the film, and as I said, film are electroactive. That means there is some conductivity into the polymer, probably by electron warping phenomena. Film are sensitive to, of course, oxidation by oxygen. In fact, if the film is conveniently dry, you can keep the film for weeks. But if in contact with a solution containing oxygen, there is a rapid reoxidation of the film. And we have demonstrated, for instance, that the complex, the polymer, can be oxidized following a two-electron process. If you do that in acetonitrile, in fact, you come back to the starting material, except that the initial chloroligand is replaced by 2-acetonitrile. Well, we have studied in great detail the oxidative oxidation of the film, and we have demonstrated that, in fact, we can see two different steps. The first one led to this dimer is the ruthenium-1 metal-bounded system with the 2-acetonitrile in axial position, and the second step led to the, as I said, to the bis-acetonitrile complex, and some isomerization occurs. I mean, in this case, you go back to the cis compound. It's a detail. More importantly, some other guy at Turku University demonstrated very recently that the partially oxidized form of the polymer has a high electrical conductivity, and they studies in detail the structure of the film as a function of the potential. Well, so how it works? I mean, the mechanism of polymerization, it's just a classical. It's a stepwise electrochemical propagation. The first step involves the injection of the electron of the bipyridine ligand, followed by a fast decoordination with remove loss of one chloroligand. There is an internal electron transfer, I mean, make this ruthenium-1 species. At this stage, there is dimerization, and the dimer itself, we have demonstrated that by studying the chemically prepared dimers. The dimer itself is more easy to be reduced than the precursor. So that's typical of stepwise electrochemical propagation. So how we demonstrated that the first step here. So in fact, We prepare the equivalent osmium complexes. The osmium is in the same column of the metal. It has the same electronic configuration, but it's an heavier metal than the ruthenium. So it's expected that the coordination bonds are stronger, and exactly that we observe. That's the typical cyclic of the osmium derivative in the same condition at room temperature. You can make easily the same kind of film that for the ruthenium. But if you use a lower temperature, minus 20 degrees for instance, the room temperature cyclic, it's irreversible two-electron processes replaced by a nice one electron transfer, reversible electron transfer. And we did some spectro-electrochemical experiment, and we were able to characterize by infrared, UV visible, the corresponding species, the transit radical anion of the osmium complexes characterized by this typical EPR system signal. Well, another characterization using also EPR, it's spectro-electrochemical experiment conducted in solid states of this complex. We use here more sophisticated ligands at the initial bipyridine, and you can see that initially at this stage there is no signal at the rest of potential, and if you potentiostate it here, you get this signal with typical of ligand-centered reduction. Some signals are also obtained by oxidation over there, and it's typical also of metal-centered in this case. Well, our material was not easy to characterize. I mean, to get a nice structure. So it was impossible to make monocrystal, for instance, for conventional X-ray diffraction. So we use a specific technique. It's high-ray powder diffraction. Combined with the modelization. So we asked some specialists in Italy, in Com and Milano, I guess. And they found this, they modelized the structure like that, and they were able to measure the atomic distance. It's around 3 angstrom, and they found that there is, in fact, a random orientation with a 4 equivalent orientation of the ligand around the zigzag chain. And this structure was recently confirmed by solid-state NMR and DFT calculation. So let me go to the catalytical aspect of the work. So, as I said at the beginning, if you want to make a nice system, it's necessary to work in a pure aqueous solution. So here is a typical signal of the film in a pure aqueous electrolyte. And the electrochemical response is quite similar to what was observed in acetonitrile. That's the oxidation of the metal, reduction of the bipyridine. It's under argon. What's happened if you saturated the solution with CO2? You can see a very huge catalytical current over there with a shift of around 500 millivolts in direction of the positive potential. So it was very impressive at that stage, and so to confirm the electrocatalytical activity of this kind of film, we investigate in detail long-term electrolysis of this kind of system, and we demonstrated that CO2 is selectively reduced following a two-electron, two-proton process into CO. And another interesting thing is that we were able to tune the selectivity of the reaction by introducing on the bipyridine ligand an electron acceptor. You change totally the selectivity. In this case, you got the formate instead the CO. And for instance, exhaustive electrolysis on the carbon felt of the film in pure water with sulfate as electrolyte. If you use the polymer with a classical bipyridine, you apply that potential, you go with the quantitative yields to CO. And if you use an ester group in this place here, at that potential, and you can see that this potential is less than the thermodynamical potential of the reduction of CO2 into formate. It's a real catalysis, and the selectivity is crazy quantitative in this condition. So, as I said, this film are quite sensitive to oxygen. So in the second step, we were thinking about to stabilize this kind of film or render them more easily handled. So we use an old techniques that we have developed in the lab since a long time ago with my colleague Jean-Claude Moutet, is there, based on the electropolymerization of functionalized spiral containing metallic complexes. So we design complexes having a group, a parallel group on the bipyridine, and by classical electropolymerization, it's an anodic one, we make film of the precursor of polypyrrole functionalized by this precursor on the electrode surface. So if, for instance, some oxygen is going into the polymer, what's happened? When you reduce, of course, the precursor, you make inside the film the metal-metal bond. So if some oxygen occurs, there is a metal-metal bond breaking, so the ruthenium 2+ is created, but in this case, it remains on the surface via the polypyrrole. And after the oxygen was going away, it's worked again. So we check that by, of course, the same exhaustive electrocatalysis in water. For instance, at that time we use a microfiber. If we did the job today, we probably use a carbon nanotube, but you know, it's 15 years ago. So that's the picture of the microfiber. You can see here the typical polypyrrole film on the surface, and you obtain exactly the same selectivity, depending in particular of the substituent of the bipyridine ligands. Okay, so just as a new light of our kind of complexes. These people at the Toyota research in Japan use our system to make one of the first photoelectrochemical system for the reduction of CO2 in water. They use a semiconducting P-type photocathode, and they obtain the photo reduction of CO2 in pure aqueous solution. So at that stage, we worked with Raymond, of course, and with a sponsor. So we go to a small device, a pilot device, using the fuel technology cell, I mean with gas diffusion, and it works pretty well, at least for a while. So it should be the end of the story, of course, but what we can do more, what we could do more with this system, we were able to have a nice system able to selectively reduce CO2 in CO of our formate. So the idea was, is it possible to hydrogenate directly the CO or formate in a bifunctional catalyst? I mean, associate at the same place and in the narrow another catalyst able to hydrogenate. So we explore two directions, an homogeneous one and a heterogeneous one. No time to develop this aspect today, so I go to the formation of a composite nanomaterial with an idea to attempt to electroreduce CO2 into more than 2 electrons, I mean, go to alcohol or hydrocarbon. So the idea was to use our polypyrrole film and to make some dispersion of noble or non-noble metal nanoparticles into the film. So how we made that? We used all the strategy made by Wrighton, as I showed you at the beginning with the viologen with palladium. The idea was very simple. We use a polypyrrole film in which the actual ligand are acetonitrile instead chloro. Why? Because the film is positively charged. And what's happened if you put this kind of modified electrode in a solution containing, for instance, this anionic complex of noble metal, you incorporate, we replace the initial anion in the film by this palladium chloride, for instance. And if you reduce in situ the system, you make a composite material of the polymer film and with particles. In fact, the tricky thing to obtain nanoparticle, it's necessary to use pulse strategy. Pulse electrolysis, for instance, this one, you apply that a potential for 1 second. And for instance, with the palladium, we obtain nice nano-dispersed particles into the polymeric film. As I said, with the palladium, that's the term picture here. And if you use a high-resolution term, you can observe the crystalline plane of the palladium. Well, what about the catalytical activity of this kind of composite material? Big change. That's without, of course, without nanoparticles. And depending on the metal incorporated, you change drastically the selectivity. Of course, you make hydrogen. And in some cases, you can observe some hydrocarbon, in particular with rhodium and copper. And with rhodium, you can observe a small amount of methanol, but the best result was obtained with the nickel and not with the regular bipyridine, I mean with, in this case, substituted by a carboxylate group, some significant amount of methanol is obtained. Well, so, yes, 5 minutes? Perfect. So, another application of this kind of polymer is not an electrochemical application, it's an application of water-gas shift reaction. It's a very important industrial process, as recalled by the right side Monday afternoon. It's the way to purify or to obtain hydrogen when you make hydrogen actually from methane, from natural gas, for instance. That's the second step of the process. And we have demonstrated that this polymer it's very active for this important water-gas shift reaction. Water-gas shift reaction is action of water. That's action of water with CO to goes back to CO2 and hydrogen. Why we were interested by that? Because initially our colleague in Yonshu demonstrated that this complex itself is active as a catalyst of that reaction, and they observed a blue-black precipitate, and we demonstrated with them that in fact the catalytical species is the polymer formed in situ during the process. So, just 2 minutes. Okay. Some outlook. So, what we are doing now with this kind of system. If we have any chance to use this kind of system for application, it's necessary to replace noble or rare metal by Earth abundant first-row transition metal. It's necessary. If you look abundance in the Earth crust by weight, there are 3 abundant metals. Of course, iron, titanium, and manganese. Titanium, for reduction, forget it. Nickel, you know, nickel and cobalt, it's very far away from the same level of abundance. And I don't talk about rhenium or ruthenium. Even for ruthenium, it's possible to obtain ruthenium from nuclear fuel retreatment if you are patient. I mean, it's necessary to wait 10 years. Okay, so we start first with iron derivative. And the most obvious was to use the corresponding complexes of ruthenium and osmium. Remember, the same column, iron, ruthenium, osmium, I mean the same atomic configuration, diatomic configuration. Problem, we spend quite a lot of time on this, but we got no success. And finally we gave up because these complexes are very unstable, even with the iodo derivative. So we shift to try to make some more stable compound by replacing the anionic ligand by a stronger one, for instance, a thiol derivative. Complexes are very much stable, but electrocatalysis under CO2 gives mainly hydrogen. It's a good catalyst for hydrogen production, but not for reduction of CO2. What does it mean? That means that probably the reduction of CO2 don't go through the formation of an hydride. So we shift recently versus manganese derivative. Manganese is a very sympathetic metal. Why? Because the ore, it's very abundant, it's easy to be treated. The ore are very rich, for instance, the manganese dioxide. And it's used from a long time by our ancestors, since you can see in the Lascaux cave, for instance, the black color of the painting was made by our ancestor using manganese oxide. So what's happened if you use simply the corresponding complexes of rhenium, initial rhenium, the famous rhenium made by Raymond? It's work, and it's worked pretty well. Got a very efficient selectivity reduction of CO2 into CO, and more importantly, I mean, beside the fact that manganese is an abundant metal, the reaction occurs at 0.4 less negative potential than the derivative. So our future objective are to make molecular cathode with that and work in a pure aqueous electrolyte, of course. So my time is over. Just last transparency for acknowledgement of people. Sylvie Chardon, she's the director de recherche of CNRS, and she's in charge now of that program in my group. My successive student, a special mention to Marie-Noëlle Collomb, who were our first student, share with Raymond. She's now director de recherche also in my group, but she shifted to the other part of the photosynthesis, I mean the oxidation of water. Some postdoc, several collaboration, special mention to Raymond, of course, and people also in Amsterdam, that's Dr. Hartl. He is a specialist of electrochemical system. And Professor Keim, I don't talk about, but that's the homogeneous system. And also some sponsor, French Navy, for instance. Because at the beginning, we don't work for the problem, to solve the problem of global warming, but for the army. And special thanks also to Volkswagen for the video. And thank you for your kind attention.
Thank you, Alain, for your very interesting lecture. And that is open for discussion. Are there questions?